Hi, my name is William Henry, and I'm a computer science major just finishing up my degree here at FSU. I'll be done in December. I currently work as a business proposal analyst for a major defense contractor. My plans are to move into some sort of a software-related type work, probably software quality right now, but I'm exploring my options. And my presentation will be on Kalman filtering. This is for my top 10 algorithms class. Thank you. This is William Henry, and my presentation is on Kalman filtering. First off, a little overview about what Kalman filtering is. It was created by Rudolf E. Kalman around 1960. Some similar techniques came from other gentlemen named Swirling and Busey in the late 50s and early 60s. This is basically all this is an estimating technique for measurable data. It uses recursion on various signals or different types of data that have noise in them, which basically means that it's not well defined what the exact values are. There's a lot of back and forth and some noise that you can't really tell specifically what the measurements are. And this estimating technique basically takes the data and calculates an estimate for what a measurement should actually be over time, as compared to the actual measurements, which may be incorrect for various reasons, whether it be time lag or problems with the data. Now, there's a lot of applications for Kalman filtering. One of the primary ones is guidance, navigation, and control, and basically all that is anything that uses an engine or usually in flight needs to be guided as far as where it's going. It needs to know how to get there, where it is, etc. And Kalman filtering can be used because a lot of the data is grabbed over time, and there are some techniques as a result of Kalman filtering that can give a much better idea about speed, trajectory, and different issues with GNC. It's also useful for signal processing. As I mentioned the noise earlier, with signals, as we already know, there are error terms associated with them, and it's not perfect, especially when two signals cross. Now, to come up with an exact data estimate is going to be impossible, but Kalman filtering can give you a good idea of what the measurements from signals should be, or come closer to the appropriate measurement. And one of the primary uses for the signal processing aspect of Kalman filtering is in radar. Now, you can also use it in economics, various types of data, whether it be inflation or unemployment data or economic growth. And it's also useful in time series analysis, not just economic time series analysis, but things like temperature and whatnot that are calculated over time. Now, Rudolf E. Kalman was the primary developer, but obviously, as I mentioned before, some other folks had similar ideas. A guy named Busey actually is often co-named on the filter with Kalman as a result of his contributions. Now, what prompted this was the need for a better technique in coming up with measurements. Sensors can only take measurements so frequently, and often there's a lag time or some type of imprecision. However, the thought is that over time that imprecision will average out, so you can filter the measurements to obtain a better estimate of the actual value. For instance, you might have a chart that goes wildly up and down and is not very centered on a continuous measurement, but if you filter it, you'll have a much smoother curve, and you can estimate future data points and even current data points a lot better if you smooth out that issue in the measurement. Now, the original application of Kalman filtering was to spacecraft trajectories. Kalman noticed the need for better navigation on the Apollo program, and that's kind of what led to the development of the Kalman filter. It's actually used today on the ISS as well. Now, the general process of performing Kalman filtering starts with a series of measurements. You'll have some type of system with known dynamics, for instance, a spacecraft. You'll calculate a weighted average of the measurements that have been taken, and you're going to weight them based on how good the filter considers the measurement to be. Now, oftentimes more recent measurements might be considered better, but that's not necessarily the case. It depends on how the filter's set up. Now, it recursively calculates newer and newer models as it goes on, and when it finds the weights to produce each new model, the covariance value is often used in finding these weights. Also, the model can be adjusted with a factor known as the Kalman gain, which basically says whether or not to favor a model estimate that it's using or to favor newer current measurements. And depending on what that Kalman gain is set at will depend on whether or not the new measurements affect the estimated values as much as the old model does. And then all the calculations are done using matrices. There's a pretty complex process to come up with the new models and such, and I won't have time to go through all that here. Now, a little bit more description of the process. Suppose we have some type of time series of measurements. For example, we might have the speed of an aircraft, or maybe we have temperature measurements over time. Now, we can only get so many measurements, usually in some sort of increments. You might be able to get 1 per second, or with temperature measurements, it might be 1 every 10 minutes. Now, obviously with that, there's a bit of a delay. And we want to get the best estimate of the actual speed of the aircraft in that instance, or maybe we want to look at the temperature, but for now, I'm considering the aircraft because it's an easier one to talk about. First, we calculate the estimated speed value. This is known as the a priori estimate. We have some model that describes some initial speed that we've already calculated. Now, from that, we begin with that, and then using both the new measurements of speed and the covariance, we can find updated estimated values for the speed. So basically what we have is an initial model estimate, and then as new measurements come in, we update the model. And these calculations are the very generic calculations listed that are needed to do the Kalman filtering. Some of these factors are used to adjust different models, and it really depends on the model, some of these choices of factors. Now, as I've described, we need to start with an initial model. Just as for instance, let's say our aircraft initial speed is 16.5, let's just say, and then that's our model estimate at least. And let's just say actual value is 20 kilometers per second or something. It's just basically, obviously the model is not going to be the same as what our actual estimate or as our actual measurement comes in at. So we take into account the new measurement and we update the model. Maybe the new estimate will come in at 18.5, just as an example. Now we keep doing this over time. We keep updating our model based on newer and newer values. And it takes into account all the old values as well. And obviously, depending on our Kalman gain and our choice of our model, that will affect how our estimated values change over time. Now, a lot of the applications of this, I've already mentioned some of them. The biggest one, guidance, navigation, and control systems. Obviously for spacecraft, Apollo being one of the first uses of Kalman filtering. That's why I listed that here. The International Space Station as well uses Kalman filtering in its guidance, navigation, and control systems. Another example would be missiles. The air-to-ground missile system Hellfire uses a GNC system that has Kalman filtering involved in it. Econometrics, another example. Time series analysis. Usually time series analysis, you're going to be smoothing out data because there's a lot of up and down, a lot of noise in the data. So you're going to have a smooth curve that you can use for trend analysis. Also for particle positions. Particles, calculating their positions and movements, notoriously difficult, so using a Kalman filter can kind of come up with a much closer estimate for the actual position and movement of the particles. Now for the final overview, basically it's an estimating method that you can take your measured values that you have over time, and you can estimate what the actual value at that time frame should be, because obviously the data has a lot of noise in it in many cases, so you can smooth out those values so you have a much better grasp of the actual speed, trajectory, or whatever it is you're trying to measure. Now, another name for it is linear quadratic estimating, and generally Kalman is given most of the credit for creating this, hence the name Kalman filtering. Some other people had various contributions. That's why sometimes it'll be referred to as Kalman-Bucy filter. Now, the point of this is to use a recursive updating model, which estimates whatever your value that you're trying to get is. For instance, you might be after speeds, temperatures, what have you. You start with the initial model, and then as new estimates come in, you update that model based on the new values that are calculated by whatever sensor you're using, and then the model slowly starts to get better and better at producing these estimates. And the theory is that these estimates will be very close to the actual values because it'll smooth out the noise. And there's a lot of different uses here, obviously guidance systems being probably the most important one, and economic data, and then particle movements, of course, would be another useful instance of Kalman filtering. And that's pretty much it. And there were some references that I used in developing this, and those are listed here. Thanks.